Okay, so today I want to show you how to properly hindcast an offset well, friction factor for an offset well, and how to use it when planning a new well. So I have two scenarios in here, and the first one is the offset well that was drilled sometime in the past in the field, and I'm interested what kind of friction factor to expect when drilling this in this field, and that means also what kind of loads to expect when drilling a new well with the same friction factors. Right, so first thing to do is to create a trajectory, and the best way to do that is go to the definitive surveys, copy them, measure depth, inclination, and azimuth, and paste here in the TDH trajectory module. So that will calculate our surveys, and we are ready to do some modeling for this particular offset well with this particular trajectory. So next thing which I need to do is to create a wellbore. So I'm interested in friction factors for 6-inch open hole in the offset well, and I've created here 6-inch open hole section and the casing and the riser, which is above that section. And since this is an offshore well, I will require the riser and conductor plus my open hole section. That's all I need to do in here. If I wanted to analyze different hole sections, then I would create a different open hole sections and different previous casing. That would be 13 and 3-inch casing and then a riser to surface. The next thing to do is to create a drill string, and that needs to be that drill string which was used to drill this particular well. So I went back to the daily drilling report and I came up with these 6 and 5/8-inch drill pipes, and then heavyweight, and then a lower BHA. Based on the reports, this is what was used, these tool joints. And for the lower BHA, what we do is we average all these IDs and the weight. We don't necessarily need to specify each sub and stabilizer and other component. It's just one long drill collar with average all these IDs and weights. Now, the important thing to do here, and that needs to be calibrated pretty accurately, is the adjusted weight. So if you know exactly what the drill pipe was used, you might want to go to a manufacturer's website and read these. Or if you have a specifications sheet that lists adjusted weight, use these, because the models will be based um, on these, and then the friction factor which will read will depend also on what kind of model we use and what kind of adjusted weights we use for the drill string. Right, so that's all we need to do here. The next part is the hydraulic system. And for the torque and drag, the rheology and surface pressure losses and bit nozzles, it's not that important. The important thing is that you know what kind of mud weight was used to drill this whole section, because the mud weight will influence the buoyancy, and the buoyancy will influence the expected torque and drag loads. Right, so once we've done that, we are now ready to specify some parameters and then run our analysis. Now, what you want also to do is to accurately specify the traveling assembly weight, because all the actual weights that the driller read through from the Martin Decker throughout the section will also include the traveling assembly weight. So that's the block and the top drive, which is added on top of the drill string weight, drill string tension. So if you know what kind of drill ship or rig was used, go to the specification and read out this value and enter in here in the analysis parameters. Now, the last thing which you will need to do is get hold of the historical pickup slack of and rotating of bottom, and possibly also torque or bottom torque values. Now you can go back to either a daily drilling report or driller's trend sheets. I think it's a better source. Or like me, I had a chart that was created at the rig site, and I digitalized that chart, which had pickup slack of rotating of bottom and rotating of bottom torque values. So once you've done this, you can either manually enter them in this table by measure depth, or you can copy paste these values from your source to this table. Right. So I am ready to analyze right now. And what we will see here is our torque and drag. So that's hook load chart. So our hook load roadmap for drilling this particular 16-inch hole section for this trajectory, this drill string, and this wellbore. And on top of these, you see plotted here slack of weights in blue, pickup weights in red, and rotating of bottom weights in green. So what we need to do right now is to calibrate this chart. And to calibrate this, we need to ensure that our green dots, which is rotating of bottom, follows the modeled rotating of bottom line. And we can see there is some discrepancy here inside the 20-inch casing, and that could be attributed either to shift friction or I could also question the quality of these pickup and slack of weights inside the casing. Maybe different speeds were used, maybe different procedure for reading and taking this pickup and slack of weights and rotating of bottom weights. So what we are interested in is here below the 20-inch casing shoe. Let me zoom in here. So maybe without these 3 points, we are calibrated pretty okay. So I would say we could use that model of the path right now. And you can see that our pickup and slack of weights are following some model lines, but also there are changes in the trends, right? So the friction factor increases around this depth, then decreases, and then increases again and decreases, and pretty much the same behavior you can observe here in the slack of weights as well. So that tells me that there was something going on in the well, that the friction factors increased and decreased. Probably some changes were introduced to decrease the friction factor. Maybe the ROP was controlled. Maybe some rheology improvements to improve hull cleaning were done. We could go back and see what changed around these depths, where the trend changes from increasing to decreasing and vice versa, and maybe do a little bit of an interpretation what was going on hull cleaning wise and what kind of changes were introduced. But for me right now, I could say that for the majority of the section, I can expect 0.3 friction factor for slack off and up to 0.25. If I want to be a little bit conservative, I would say 0.3 for both pickup and slack off. So that's the friction factor, which I know right now was experienced in the past in this field. Based on this particular well, I could run a couple of more wells. Also, 16-inch hole section, I do separate investigation, separate hindcasting for 12.25 and 8.5-inch hole sections. But for now, I can assume I should not see more than 0.3 friction factor if I want to drill in the same field with the same technology, with the same mud and similar drilling assembly and similar tortuosity. So if I take a look right now at the surface torque chart, you will see the off-bottom torque right now is plotted with a line. So again, at the beginning of the whole section, it starts off with 0.25, then levels out at roughly 0.20, and towards the end of the section, there might be some additional lubricity or change in the formation, and we're down to 0.15. So again, to be on a conservative side, I would say that 0.20 is something to be expected in the next well throughout the section. And the next thing which I need to do is come up with a scenario for the new well that will be drilled. And I've already entered here the planned trajectory, planned wellbore, casing setting depth, strings, and everything else. And I think my mud weight right now is 9.7. Okay, and I'm ready to again hit analyze button. And my traveling assembly weight changed right now because I will be using a different rig with heavier traveling assembly and I'm ready to analyze. So from the past well, from the hindcasting, I know that I will be following roughly 0.3 friction factor lines, which is this for pickup and 0.3 for slack off. I'm also plotting here 80% of the tensile load, tensile limit body, sorry, and I can see that for 0.3, I still have a plenty of overpull available between my load line and my tensile limit. For slack off, I don't see any lockup, I don't see any buckling going on. I could go to the profile analysis for 0.3 friction factor line and see for slack off and see whether I'm buckling. So for 0.5, I will be buckling my pipe. For 0.3, I'm okay. There's no buckling going on. I'm not touching this sinusoidal or helical buckling line. And I can go again back to driller analysis and select my torque plot. And from hindcasting, I know that I can expect 0.2 friction factor for the torque. So that's my load line right here. I'll end up at TD with roughly 23,000 foot-pounds of bottom torque. And that's way below my makeup torque, which is roughly 90,000 foot-pounds. That's a heavy 6 and 5/8 inch drill string, which, you know, is plenty. Now I could go do the same for 12 and a quarter and 8.5 inch section and check whether what is my friction factor and whether my planned well load lines for these hindcasted friction factors is within the system limit. And that's basically an exercise which is good to do for any new wells being drilled or planned to be drilled in the field where we don't have a history from, or have a history from the wells that were drilled in the past, and we don't necessarily have everything hindcasted yet, or the experience is lost. And that's pretty much it. Thank you very much.